these are coordinates that are best served when, or to use when whatever the equation you're working with has spherical attributes. I mean, so if you're talking about like a bounded region, like a plane over a rectangular base area, that doesn't sound very much like a sphere, so it wouldn't necessarily lend itself to spherical coordinates. But if you wanted to find the volume of a sphere, that's very much a sphere and very much would apply, or very much a situation where spherical coordinates would apply. All right, let me get rid of this stuff. It's kind of distracting. So more so for me, because I'm worried that I'll just forget what class I'm in and start teaching the wrong stuff. So anyway, or just go off on a mega tangent, which could be interesting, but that's kind of a different story for a different moment in time. So definition in spherical coordinate system, a point P in space is represented by the order triple rho theta phi, where, and there are some books and some people, I guess, that reverse the last two, rho phi theta, right? And there are some people that reverse them, but use the phi to represent what the theta represents, and use, and vice versa. So it's kind of strange that there isn't more uniformity in the way that this is all represented. But as long as you know what each one represents, then you're fine. All right. So I'm gonna, it's all written there, but I'm gonna jot it down here anyway. The rho, funky looking P or HO Greek letter, that represents the distance from the origin the theta represents the angle in the XY plane. All right, so think unit circle. The unit circle seems to keep coming back over and over again. It's crazy. And then the phi represents the angle from the z-axis. All right, distance from the origin is your rho. All right, so it's basically taking on the role of the radius. So why don't we call it r for radius? Well, we already used r. Well, that it's not as simplistic as that. Or that's an overused term for me anyway. It's not as simple as that. It's, yeah, r is already used for the radius in polar coordinates, but the issue here is that we want to relate the polar or cylindrical coordinate system to the spherical coordinate system. So in order to do that, we can't use the same variable. I mean, I suppose we could use a capital R, but we opted to go for the Greek letter rho. All right, so that there you go. So that's the justification for it. And you can see in the diagram below that there's some simple relationships here, but one thing that might pop out at you is that you got a line segment that's labeled R and a line segment that's labeled rho. So there's definitely a geometric reason why you would not necessarily want to call the distance away from the origin the radius. Now you can think of it that way, but it's going to be abbreviated with something else, instead of the letter R, right? So now this is kind of a weird diagram, but it's kind of the best one I could find in terms of I don't know how to describe it other than to say it's a simple diagram, but it has the complexity that we need in order to get the job done. The issue is, in a lot of ways, it might be too simple. All right, so it loses a little bit of the perspective nature because it's kind of hard to see unless you look at it carefully that this is a right triangle. What you see with those dashed line segments and that hypotenuse row, that's a right triangle that's standing with its base in the XY plane, with row just kind of living out in space. Right. So if you can kind of look at it from the right angle or from the right perspective, then you can kind of get a truer sense of what's going on there. Right. So if I overlaid it with the grid for the XY plane, it might make that aspect of it easier to conceptualize, but then it's too busy of a picture. So I kind of just sort of live with this one. But if we look at this as we have the XY plane that's flat on the surface, like if you're looking at this as a structure that's on a table, right? In a classroom, I actually have I put it together. I went to Home Depot. I bought some couplings, and I put together some PVC pipes, and I made a three-dimensional set of axes, and I took a piece of string with a little ball at the end of it, and that's my point in space, and I just kind of hold it out in space. I mean, I'm asking you to imagine this construct that I can't really show you because even if I wanted to, it's on campus, it's locked away, can't get to it. But that's really what we're looking at. That point is just kind of floating around in space, right, with variable components, right? But there are some relationships that we can pull from this. There's some simple ones. I mean, this one right here, I'm just trying to highlight it. I'll highlight it and then I'll erase it. Unless it comes out awesome. All right, kind of came out awesome. I never successfully got that to work in the past. Honestly, because it was only until this semester, or it wasn't until this semester, that I realized that there was like an autocorrect to the pencil. I had no idea, so I was just kind of winging it. But this right triangle, right triangle to right triangle, no matter what coordinate system you're working in, has two legs and a hypotenuse. Those two legs, Z and R, will give you the relationship of Z squared plus R squared is equal to rho squared. All right, so let me get this mouse head out of the way. So that's good. We already got a simple relationship. All right. Now, if we were to extend that point to the Z-axis, we could get even more information out of this. So I'm going to drop an altitude to the Z-axis. Well, it didn't quite go as I planned it, but I'll take it. Oh, that definitely didn't go as I planned it because I wanted this tool. Why is that happening? That's weird. Okay, well, let me just stop messing with it. So I'm dropping an altitude here. We have some distance Z. And I have a hypotenuse, and this angle phi, the relationship between Z, rho, and phi is a cosine relationship. So I could say that cosine of phi, as best I can make it, is equal to the adjacent side Z over the hypotenuse, sorry, hypotenuse rho. All right. So the pollen's getting to me already. So it's going to be water and cough drops for me. And probably Flonase before it's all over. All right. So I could do a couple of things now. I can do a substitution because I see now that rho would be equal to Z cosine of phi. All right. And so I could actually pop in the rho for rho squared, just square these two components and go from there, see where that takes me. Right? Or I could just live with this as a relationship between rho and z and phi. You know, that's a possibility. But we don't want to lose sight of the fact that we do have that base region to play with here, right? The xy plane. All right, so all of this. So here's my x-axis. Here's my y-axis. Okay, that, let's see if I can make that fit halfway decently. All right, best I can do. All right, so I got my x-axis and my y-axis. All right, now if I take that out and rotate it, change the perspective so it's your ordinary xy plane in 2 dimensions. Right, then if I have a circle, a circular movement along or around that coordinate plane, any angle along that circular path starting at the origin, or I'm sorry, starting at the x-axis, starting at 0 degrees, would be defined as theta. Right. Let me actually tuck that in a little closer. Theta. All right, whose components are some value x and some value y. All right, and having a hypotenuse of r. All right, so that's what this part of the diagram is really saying over here. All right, so let me get rid of this. Let me make that look a little nicer. All right, that looks worse, but I'm going to pretend it in my mind that it looks nicer. All right. So, oh, sorry, I circled the wrong thing when I said we're talking about this part. It's really this part. All right, so let me bring in another color. I'll go straight to black here, and I'll drop an altitude from this location to the x-axis, the positive x-axis. I'm going to try to make it look as perpendicular as possible, best I can. Here we're going to have some value x, some value y. So the relationship, as we know from 2-dimensional studies, is that x squared plus y squared is equal to r squared. All right, so we have that relationship to work on. All right, so now we have a way in which we could determine the rho value. I mean, we have a way that we could determine the z value if we want. You know, we could solve this equation for z, you know, and make a substitution that way. Right, we have a way to swap out the r squared here with x squared plus y squared and get it strictly in terms of x, y, and z on the left-hand side. And that's an important relationship because x squared plus y squared plus z squared is equal to that is the equation or the model used to find the equation of a sphere with the center at 0, 0, 0. Right, so all of that information just coming from a quick look at a picture. All right, so if you take a look at all the rules that you have on the side here, maybe they're a little less daunting because they're all just coming from what we determined based off those simple relationships. So the first one, the x is equal to the rho sine of phi cosine of theta. Well, that's kind of tricky because it looks like it sort of comes out of nowhere. But if you think about it, what we'd have to do is figure out a way to represent this location in terms of those spherical coordinates. And so how do we get there? We can get there by following this path, x, y, followed by z. But if I want to be able to think of those values in terms of spherical coordinates or those other measures, the rho, the theta, the phi, then I would need a different way to define the x value other than to say, it's just x. Well, we know that x is equal to r times the cosine of theta. Okay, we have a relationship between the r value, z, and rho. We have a relationship between z, rho, and cosine of phi. So all of these different relationships would build you towards those rules. So I didn't want to get too far into deriving them all because, I mean, even though it's kind of fun, it's really more of an exercise in algebra than anything else. And so, you know, we would list out, okay, well, what do we know about theta? We know theta is equivalent to the inverse tangent of y over x. We know it's the inverse sine of y over r, inverse cosine of x over r. We know that y is equal to r sine theta. All of those put in a pot together, mix it up, and you come out with these formulas with a little bit of algebra. All right. So what we want to do is work off of these formulas so that we can easily convert back and forth between polar, or not even back and forth anymore, among polar, rectangular, and spherical, or cylindrical, rectangular, and spherical, either way, because as you know, the cylindrical coordinates are just polar coordinates with height, right? So you'll see that I highlighted a rule here, or a set of rules. This is an important relationship. So R is equivalent to rho sine of phi, right? And again, that comes from this triangle, or this triangular relationship. R is equal to rho times the sine of phi is coming from, and if I'm gonna try to, I might want to clean that up a little bit. We can come up with the sine based off of the location of phi, which would be the opposite over the hypotenuse, right? So sine of phi is equal to the opposite side. That opposite side, excuse me, is parallel to whatever the y value is, which is going to give it a value of y. Right? Sorry. Get another sip of water and a cough drop. I think I'm right. So, long story short, you're gonna, because I just said I was going to get into all the algebra, but now I find myself doing it. You have, in order to get to this location, a movement along x, a movement along y, and a movement along z. These y values, even though they don't look like it in my diagram, are going to be parallel to one another because they all represent a movement along z. The issue is it just doesn't look like it because it's a terrible perspective drawing. Basically, it started off all right, but it's now not all right. But the opposite side would be y, with the hypotenuse being rho, and then with some substitutions, you can get to these relationships. All right. So, geez, I can't. I'm trying to That might have been the one. So we have r is equal to the square root of x squared plus y squared from way back when. R is equal to the rho sine of phi from this page. So they're therefore equal to each other. So that's where this relationship comes into play. Now, you might look at this and say, well, it's just another rule. This actually ends up being the single most important rule when it comes to making conversions to get you into a convenient form to integrate with spherical coordinates. All right, so let's actually hop to the next page. Oh, I see that there is a question or a comment in the chat. R over. Oh, you know what? You're right. It's not Y. I highlighted the wrong dang thing. I pointed out the really wonderful perspective drawing that became terrible, and I highlighted the wrong thing in doing so. It should have been the R value here. That's parallel to this. These two are parallel, and let me use ordinary parallel symbolic notation. These two are parallel and congruent to each other. All right, so parallel and congruent. And so therefore, this is the same as R. So this is congruent to R, which in turn is the square root of x squared plus y squared. Sine of phi. Then you have your rho either form. And then when you solve, you should end up with the appropriate relation. And hopefully this time I didn't screw it up. Let's see. Right, because they're, yeah. So I'll actually put a little room in here. I don't even know why I moved this down to begin with. I'm going to do that. So R is equal to rho sine of phi. And rho sine of phi is equal to the square root of x squared plus y squared. All right. Thank you for that. So we're going to be relying on these rules pretty heavily. And so therefore, put a star on this page. I don't know, somehow draw your attention to this page, draw your own attention to it when it comes to taking a test. Just make sure you have access to this page because all these rules are going to be pretty helpful. For these examples, what I did was I just jotted the important rules on the side, just so you have them, including the most important one. But, and honestly, you might look at it and say, well, that one's, how is that any more important than the other? It's important because when you get into the examples that kind of lend themselves to spherical coordinates in multiple integration, you see that it ends up being the case that relationship, the rho sine of phi, the square root of x squared plus y squared, without having to bridge the gap over to cylindrical coordinates, or without having to use cylindrical coordinates to bridge the gap between rectangular and spherical, it becomes a really important time saver. All right. So just like we did with cylindrical coordinates, I thought it'd be a good idea to talk about the points themselves first, then get into some equations, and then from there get into the multiple integration aspect of it. All right, so our spherical coordinates, rho, theta, phi. Yeah, and kind of got in the habit throughout the day of making little sigmas because it's kind of in a stat mindset all day. So my thetas may mysteriously turn into sigmas at some point. If that does, you'll let me know. All right, so we're converting these to both rectangular and cylindrical coordinates. Well, we'll convert them to the type of coordinates that it makes sense to convert them to first, and then we'll convert them over to the other type from there. All right, so our important rules, and it kind of makes sense to start here. Rho sine phi cosine theta is the value of x. All right, x is equal to rho sine phi cosine theta. All right, and rho sine phi sine theta is the value of y. And then z, no longer like it is the case in cylindrical coordinates, z is rho cosine theta. It's not the case that z is just z because there is no z in our cylindrical coordinates. However, once we figure out z in rectangular coordinates, we will have also figured out z in cylindrical coordinates. All right, so this will get us over to rectangular. All right, so this will get us over to rectangular. You can make it work with Desmos. It's up to you. If the numbers are friendly enough, then you can figure it out. So rho sine pi over 6, cosine pi over 3. Those are very friendly. So 8 times a half times another 1/2. So 2. Half of 8 is 4, half of 8 again. Half of 4 is 2. Y is equal to rho sine phi sine theta. So 8 sine of pi over 6, sine of pi over 3. So it starts off in a similar fashion, 8 times a half, but now it's multiplied by rad 3 over 2. So it's going to be, well, it would be 2 if it wasn't for that radical 3, but that radical 3 is there, so 2 radical 3. And z, rho cosine of phi, so we're looking at 8 cosine pi over 6. So 8 times rad 3 over 2 is going to be 4 radical 3. So our rectangular coordinates, x, y, z, would be 2, 2 radical 3, 4 radical 3. Now we could just take a quick look at the graph here, which plots the point in space without any kind of real labeling. But it is the plot of the spherical coordinates 8 pi over 3 pi over 6. Right? The way I did it was I actually, and to the best of my knowledge, unless there's some code that I don't know, I actually just define x, y, and z, my coordinate values, as rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi, and then use sliders for rho, phi, and theta. Right? I have that I had that applet somewhere. I just got to look through my stuff. I can put it up on Blackboard, but we're not going to be converting coordinates very frequently. We're going to be converting entire equations. So it's something that, you know, it's for the sake of knowledge rather than the sake of getting stuff right on the test. So it's not the most pressing priority at this point, but I'll get it to you. That's at some point in the near future. I just got to remember to do it, as always. I just put it on my list of things to do. Spherical coordinate applet GeoGebra upload Blackboard. So spherical coordinate applet GeoGebra upload Blackboard is what came up, whatever. I don't doubt that I'll know exactly what that means when I go looking, so it's fine. All right, so if I go 2 units in the X direction, now you'll see here that the labels are kind of askew. I got X going off this way. So that's 2 units along this path. I'll use different colors to make it pop a little bit. So 2 units along this direction, 2 radical 3, 2 radical 3 along the Y direction. So the Y direction would get me, if I'm going around if I'm going 2 radical 3, I'm going around 3.5. So here's where 3 would be. 3.5 would be about right here. That's this distance roughly. Yeah, kind of in the neighborhood of that base point. All right, so we're looking good there. And then I think the last one was 4 rad 3. So that's about a little shy of 7. Yeah, that looks like it could be 7 units up. I mean, here's 5, 6, 7's probably about right here. So just kind of translate. Yeah. All right, so that works. Definitely. I mean, assuming that graph is right, and as in representative of those spherical coordinates, then these coordinates are, there's no reason to doubt them. Let's put it that way. Now, to get it to cylindrical, we can go one of 2 ways. We can use relationships that would convert directly from spherical to cylindrical. And that would be these bad boys. Or we can go with the rules that we already know for converting rectangular to spherical. It's it depends. It depends on the situation, right? Because if you don't have to figure out rectangular coordinates first, then these formulas aren't that bad at all. Right? Now, if you take a quick glance at them, you see that we really have no work to do here. Or at least no new work to do. All right, the R value is rho sine of phi. All right, R is equal to rho sine of phi. Well, we have that. We have that in a couple of places. We have that here. We have that here. All right, that's the first 2 entries. All right, in both of our X and Y computations. So R is going to be equal to just those 2 values multiplied. R is going to be equal to 4. Theta is equal to theta. Right? It's theta for a reason. You know, that theta value in the cylindrical coordinates is the same as the theta in spherical coordinates. We changed the R to a rho to allow for the change from radius in the context of cylindrical to radius in the context of spherical, but we didn't change the meaning of theta. So that's still pi over 3. And z equals rho cosine of phi. Well, we figured that out, but even if we didn't, it wouldn't have been difficult because that's the easiest of the computations to perform. All right, and that's your 4 radical 3. Right? The z value in rectangular is the same as the z value in cylindrical, so 4 radical 3. So your cylindrical coordinates will be 4 pi over 3, 4 radical 3. Okay. So that's a little taste of the coordinates and conversions. But we want to be able to do this. I mean, you already see 2 and 3 looming. You know, in 2 is not too bad, because you see the first one right off the bat. Oh, that's fun. First one right off the bat is taking rho and setting it equal to 13. Well, rho squared is equal to x squared plus y squared plus z squared. So I can take this and actually square both sides and come up with rho squared equals 169, which is x squared plus y squared plus z squared is equal to 169. That's a sphere with radius equal to 13. All right. And that's great news. That took a pretty complicated equation in rectangular coordinates. Really, think about that. If you were to solve that for z, it would be 169 minus x squared minus y squared all under a radical, plus or minus. If you were to put it in cylindrical coordinates, it would be 169 minus r squared all under a radical. You know, either way, it's not pretty, but rho equals 13. That's not bad at all. All right. So when you're dealing with rectangular coordinates, anything that's rectangular should be defined by constants, or should be in its simplest form defined by constants. Right? I can create a rectangle with just constant values in the rectangular coordinate system. In the spherical coordinate system, I can create spheres. So spherical coordinate system, I can create spheres with just constants. And the polar coordinate system, I can create a polar equation with just a constant. You know, a simple circle, you know, based off of the circular path, the polar coordinates, well, I should be able to define a circle with just a constant, right? The most basic geometric figure in each of those systems corresponding with the constant representation. Right? So, I mean, if I somehow came up with and honestly, I never thought to do this, but if I came up with a trapezoidal coordinate system, you know, where everything is based off of a trapezoids, you know, but, you know, trapezoids are really just triangles, you know, a bunch of different triangles, but you'd like to think that you'd be able to come up with a graph of a single trapezoid, of a basic trapezoid, using just a constant in that system, right? So that's really what this is all coming down to. Now, in some situations, it's going to be more troublesome to work with spherical coordinates, because if the problem doesn't lend itself to spheres as a base component, then you're kind of spinning your wheels for no good reason. All right. Now, part B, we have theta is equal to 2 pi over 3. Now you see these important rules. We've already used 3 of them. The one that's kind of looming large is the one that we haven't used yet, and that's the rho sine of phi. It doesn't seem to apply just yet. All right, but we do know that if we want to convert the theta into the rectangular coordinate system, well, we don't really have to worry about going from the spherical coordinate system directly to the rectangular coordinate system, because we know that theta is the same whether it's in the rectangular coordinate system or if it's in the spherical coordinate system. All right. So what this is saying, and really just the absence of the other variables is really kind of dictating what's happening here. This is going to be theta is equal to 2 pi over 3, okay, that's true for all values of rho and for all values of phi, all right? So it ends up being kind of a conceptual realization just as much as it is a, an analytic or algebraic one. All right, so you can look at your rules and see what's going on here, but you don't really see anything unique to just the theta, right? So, except to say that theta is equal to theta. So what we could do is we could go back to our knowledge of cylindrical or polar coordinates and say that theta is equal to the inverse tangent of y over x. All right. So since theta is equal to 2 pi over 3, perhaps equal again the inverse tangent of y over x, take the tangent of both sides, we're looking at y over x is equal to the 2 pi over the tangent of 2 pi over 3, which is going to be negative radical 3, which is going to be y over x equals negative radical 3. Right? So if we know that theta in spherical and theta in cylindrical are going to be the same, then we're really just assuming, okay, well, we've already mentally made the shift from spherical to cylindrical. Now it's just a matter of converting from cylindrical or polar over to rectangular, and we get what appears to be a linear equation, but it's a surface. So a linear equation in 3 dimensions is going to be a plane. Right. But I mentioned this before a few minutes ago, that it's just as much a visual representation as it is a an algebraic or substitution related concept. If you were to take this and say, okay, well, what am I doing really? I'm taking 2 pi over 3. Let's see if I can, try not to apologize for my diagrams anymore because I know that gets old. But we have x. I'll just make like weird grunting noises every time I screw something up. So x, y, z. Here's 0 degrees over here. Here's pi over, or 0 radians, pi over 2 radians. So you're talking about 2 pi over 3 being somewhere in this neighborhood. But it's happening for all rho and for all phi. All right. So that the only thing that's going to be constant is that angle along the xy plane. But the distance along it can extend forever. So if I make a point, let me make a thick point here. So the distance from center along that angle is infinite, as is the angle that it's going to make with the z-axis. I don't why I labeled it y. I have no idea. I'll just leave it labelless. But this angle is also infinite. So if it is, then it could travel all the way around in circular paths. So you'd be like, oh, isn't it going to be a big circle? Isn't it going to be a really big, giant circle? If I can go spinning around the z-axis as much as I want, that was fun. Well, yes and no. Because what happens is, when you get into the definition of infinity, things start getting a little dicey. Because, yeah, it's a theoretical construct, but if you can expand, you know, like along the X, let's say you're just living in the XY plane and you have a circle that's increasing its size or increasing its radius. I could even do that in decimal right now. Okay. So we would say we have, I'll keep it simple. I'll keep it in rectangular coordinates. Okay. So let's say you have x squared plus y squared equals, well, let me do, I can't even remember. Yeah, r squared. Okay, and I'll add a slider for r. I'll make this 0 and I'll make this like 1,000. And actually I'll make it less than or equal to r so it fills it in. All right, as this expands outward, in terms of, you know, the x and y values, as the x and y values get larger and larger, it kind of happened quickly because I probably went a little too crazy with my radius. I could zoom. Let me actually start off with the standard window. I'm going to zoom out a lot instead of radius of 1,000. So let me get at least 500 there. All right. As I start expanding outward, my circle gets larger and larger. I think that's obvious. But what's happening is, yeah, it's covering more and more area in the XY plane. Eventually, its impact is going to be indistinguishable from the impact that an ever expansive plane would have, or an ever expansive triangle would have, or an ever expansive picture of a black dot would have. You know, it doesn't matter. You know, that one was weird, but you know, it's going to have the same impact. So it's essentially going to be a plane anyway. So just because it's expanding outward in the circular path doesn't mean that it's not going to converge and have the same impact that an ever expansive rectangle would have. You know, it's actually going to have that same relationship. All right. So algebraically, you get a plane equation, you know, because again, we're looking at surfaces, it's in 3 dimensions. So we know when we're looking at a linear equation in 3 dimensions, we're looking at something that's going to be the equation of a plane. All right, but that phi, you got a nice little phi here. Phi is equal to the pi over 4. That's going to be an interesting one. Now, we have that relationship that allows us to incorporate phi into the calculations, converting us from spherical to rectangular and then spherical to cylindrical. But what about spherical directly to rectangular? I'm sorry, spherical. No, the other way around. Rectangular to spherical. All right. So that would be this one, the arc cosine. All right, so still haven't used that really important rule that I said was going to come into play yet. So you know it's coming. All right, so we're looking at this one. We have a relationship between phi and x, y, and z such that if I replace the phi with what it's known to be a constant value, you know, we're going to get something. It's just a question of how hideous it's going to be. Let me just trim this down a little bit. And if it seems like I'm kind of belaboring this topic, I'm definitely spending a lot more time on this conversion stuff and the theory behind it than I did with all the other stuff. It's just because I've experienced too many instances in the past where people just, you know, it's just a wild guess when it comes to setting up their integrals. to convert into spherical coordinates. And I think it's the only thing I can come up with is that it's a poor understanding of the underlying structure to begin with. So figure if I spend a little more time on it, maybe it'll play out the way I want it to, which is like true and complete understanding of the concept. Right. So I am going to skip a step though and take the cosine of both sides. If I do that, that gives you, it releases the z over the radical. So it gives you z equals, cosine of pi over 4 equals z over x squared plus y squared plus z squared. Now it's in rectangular form, but it's not really in any kind of recognizable rectangular form. So let's clean this up a little bit and see what's going on here. All right, cosine of pi over 4, we know that's radical 2 over 2. So we're looking at z over the radical. So I'm just going to copy paste it. We got radicals on both sides, so let's square it up. Radical 2 over 2 squared is 1/2. Square the other side, you're going to get z squared over x squared plus y squared plus z squared. All right. So we can simplify, we can clean it up a little bit. When we do that, we'll be looking at x squared plus y squared plus z squared is equal to 2z squared. Then we could bring the 2z squared over to the left-hand side, and we'll get x squared plus y squared minus z squared is equal to 0, which might have some familiarity to you. You're looking at a hyperboloid, right? But if you didn't know or you weren't sure, Desmos GeoGebra, sorry, it's a good resource for that. All right, so we're looking at a hyperboloid of one sheet. All right, so now this is a triangular hyperboloid, which is good because you're looking at if you think back to like conic sections from pre-calculus, if you've ever saw the diagram that they sliced up in order to create the conic sections in 2 dimensions, your ellipse, hyperbola, parabola, and circle. It was something like this that they used, and each part of the this type of hyperbola is a right circular cone. And so you do have some geometric relationships that are at work here. And so it's kind of cool to see that connection. Right. So it takes a little doing, but you're able to recognize these things. And because of that, kind of trim down the amount of work that needs to be completed. Like, for example, if I said, find the volume contained within the spherical equation phi equals pi over 4 over this interval, that interval, whatever, if you know that that's, hyperboloid. If you know it's a hyperboloid and it's circular, and so it's got the linear components, then you can use formulas for like for a multiple choice question. There's no reason why you couldn't use a geometric formula to come up with that. Right? That's part of the fun. Is it r cosine of r? is it r cosine of z? Oh, 0 over rho. So that's this relationship. So that's coming from this guy over here. Which would, if you're solving it for phi, it's going to be phi. Oh, I almost made a delta. Phi is equal to the arc cosine or inverse cos tan. This is how my day's going. Inverse cosine of z over phi. But since we know, based off of substitutions of some earlier relationships, like for example, x squared plus y squared is equal to r squared, we know that rho, well, I'll say rho squared first, is equal to x squared plus y squared plus z squared, which in turn means that rho itself is equal to the square root of x squared plus y squared plus z squared. Yeah, no problem. Sorry. It's at the point now where, like, I'm the kind of person that welcomes wearing the mask on a daily basis because then the pollen doesn't bother me. Pre-pandemic, I would get my car. I still get my car washed very frequently. I got the Splash car wash package. I get my car washed all the time just because the pollen is just insane. And so I open my and when the sun is shining and daylight saving time happens and it's like the sun comes into my house at the right angle. Every time like I open my backpack, I can see all the pollen getting kicked up into the air and all that stuff. And I'm like, this is brutal. So I was trying to like do the right thing and save on energy, have the window open, and I'm just paying the price right now. I'm sorry, and it's just killing me. It's gotta be not doing much better for you all. I mean, so anyway, evaluate the triple integral. Now, this is not going to involve any conversions because everything is strictly in terms of rho, phi, and theta. What we're going to have to do is get to a point where we can actually make the conversion so that we can get into this simpler form. Now, I could show you what this would look like in rectangular coordinates, but I'll give you a little taste of it just by saying, if I were to take the rho sine of phi that you see over here, this rho sine phi, use the orange highlight. I could use that to swap this out, right? But then I'd have to multiply it by another rho. Right, I have to multiply by another rho, which is the square root of x squared plus y squared plus z squared. So I would have to take this and multiply it by the square root of this in order to get a rectangular equivalent of that. All right, then I'd have to convert all the bounds, which if I'm willing to go in rectangular form, I'm not overly concerned about that. But the act of integrating that monstrosity of an expression is what would deter you, hopefully, from working in rectangular coordinates. So the purpose behind this question is to actually show you that it's no more challenging to apply the concept of multiple integration in spherical coordinates as it was to do it in any other coordinate system. All right, so it's a definite integral over the interval. In fact, it's a lot easier. Let me include that component there, because you'll notice that all the bounds are constant. If you have a set of conditions in a volume question or otherwise that lends itself to spherical coordinates, it should work out that your bounds are constant. Right, so that makes things beautiful. So, and I will show you where this construct comes from in a sec, but that's kind of the basis of all of it. Right. So integrating with respect to rows, so 1/3, let me get a thicker pen. 1/3 rho cubed sine of phi over the interval of 0 to 1. All right, we're subbing in for rho. So I plug in a 1 for rho, I'm going to get a 1/3 sine of phi. If I plug in a 0 for rho, it's going to cancel, so that's gone. So now I'm up to the second level of this shibbity bangity boomity boppity boomity boom. That's what happens when I'm not feeling well. I start saying weird stuff. But in my mind, it's fun and hilarious. By the way, the word of the day is simple. I meant to say that before, but I had said it like repeatedly over a short period of time, and I thought to myself that would be a great word of the day. But then I just forgot to say it. But I didn't forget for too long. So now I'm going to find the definite integral of 1/3 sine of phi d phi, which I could do in the calculator, but the antiderivative of sine is negative cosine, so that's not too terrible. So negative 1/3 cosine of phi over the interval of 0 to pi over 2. You know, if you're not confident, then definitely put it in the calculator. But if you are pretty confident, then, you know, do it by hand and then check it on the calculator. If you do it right, Desmos can handle multiple integrations with with constant bounds, but it's so inconsistent based off of what conditions need to be in play that I don't even bother teaching it, because it works. It doesn't work way more often than it does. All right. So I'm just going to tease that out there and then just kind of drop it. All right. So 1/3 cosine of pi over 2. Well, that's the same as saying, well, cosine of pi over 2 is 0. So 0 minus negative 1/3 cosine of 0. Well, that's not equal to 0. Two negatives make a positive. And so we get a result of 1. I'm sorry, third. Right, cosine of 0 is 1, but then it still has the multiplier of 1/3. Right. So then the last little ingredient here is the thetas. So I'm going to integrate over the interval of 0 to 2 pi. The constant value of 1/3, the theta, the antiderivative of 1/3 with respect to theta is theta over 3, or 1/3 of theta, either way, over the interval of 0 to 2 pi, which is going to give you a 2 pi over 3. So not a challenging process. It's easy for you to say. Yeah, I mean, as integrals go, you know, there's a lot of cases where you kind of, you know, have that differing viewpoint between student and teacher and think, well, just because you say it's easy doesn't mean it really is. But, you know, if you struggled with integration in Calc 2, it probably wasn't because of this type of integration. It was probably because of things like, you know, partial fraction decomposition and you know, integration by parts and trig substitution, all the you know, the chapter in whatever textbook you're using, they usually call it techniques of integration. And you're like, oh, okay, that sounds great. I'm going to learn some techniques. What you didn't realize was that you're going to learn like 4 techniques and spend like a month on it. Right? Or at least that's how it should have been, but it doesn't always play out that way. You know, sometimes it's like the demonstration of an example or two. My classes too. It's just time is an enemy there. And it's like, oh, here's an example. Here's another example. Now you got it, right? Okay, good, because you're going to need this in every class you take after this. And it's like, oh, well, best of luck to you. Yeah, it's unfortunate, but that's, and especially when you think of all the fluff that you learn along the way, it's like, probably should have spent more time studying that. You know, it's unfortunate, but the fortunate to flip that coin over to look at the other side of that coin, I should say, is that if you appropriately convert into spherical coordinates, you're not going to have to worry about those crazy techniques of integration, right? Not even use substitution, right? So that's the thing. You know, if you do it the right way, most, if not all of it, can be done either with the calculator or with the heavy support from the calculator. Right? So I'm going to stop that recording. I'm going to start a new one because that's my new kick.